Hello. I'm recording this for the third time. It's so tiring. Anyway, um, I think I came out with an alternative technique for writing LR parsers. I'm not sure if I haven't made any mistakes. There may be something that I thought wrong, but at least as far as what I thought of and what I implemented, um, the parser kind of works. So I'm just hoping that it works. And I'm hoping everything is fine. Anyway, what I thought of is just an alternative way to implement an LR parser, and it has, as is the case for the any LR parser known currently, it has asymptotic time complexity and space complexity of ON, where n is the length of the input, and it receives fixed grammar. And the difference between this alternative technique and the traditional technique is that it builds quote unquote tables as you parse the input. So, yeah, that makes it simpler to write and simpler to understand what is going on inside the parser. So, there's nothing new theoretically. Yeah, known time and space complexity, just making it more practical to write and reason about. And I'll show you how to write an LR1 parser, but I think it's trivially generalizes to LRK. Just makes this base estates a lot more. And but yeah, the generalization should be trivial. This doesn't prove that a grammar. Okay, so this parser doesn't prove that a grammar is LR. For those who don't know, Bison, for example, is an LR parser generator, and it can actually prove for every string if the parser has a conflict or not. So it can prove that a certain grammar is LR for every given string that conforms to the grammar. This parser doesn't. So because it builds tables as you parse the input, it can only detect conflicts when a specific input is given. So Bison is useful still, and you can use Bison to prove a grammar is LR. Then, handwrite the parser for that grammar using this technique. And for the sake of simplicity, I will assume that there are no empty productions. I'm not sure if you're able to modify this technique to support that scenario. And at the same time, I'm not sure if empty productions are useful in real world grammar, but yeah, I'm not sure about this. Maybe someone else will figure it out. Okay, so for some context, let's talk about shift-reduce parsers. We will assume that we will assume that the LR grammar can be parsed by a shift-reduce parsers, and we will talk about shift-reduce parsers. This fact is proven by Knuth a very, very long time ago, and for more information about this context, you can see the Wikipedia page for LR parser, where it explains a lot about how LR parsers parse a certain grammar. But the takeaway for this talk is that it uses a stack, and let's see. It uses a stack, and it's like this, and you issue actions like shift or reduce according to a given rule, and that will change the stack state accordingly, and in the end you will get a parsed result. You can read this section for more context. You don't have to read this section because this what I'm going to show you is different from this approach, but I think reading this section and understanding this section will be helpful for understanding this talk. Now let's parse a simple grammar. So the grammar has non-terminal symbol expression, term, and value. This grammar also has terminal symbols, that has star and ID and literal and plus, and the productions are given at the right, without but without this new production. These are the original productions. So these 6 rules are the original productions of the original grammar, and the start symbol is expression. Given this information, we sorry, I should have done this earlier. We know that the grammar is LR1. You can write a parser that can parse only given the parsed input and the look-ahead symbol, and can correctly parse the whole string. Okay, we will actually explicitly build a parser that parses this grammar, so you can see about that. It has left associative grammars operators. For example, this rule, term produces term times value, is left encodes this star and times operator that is left associative, because you produce this and then you can produce this once more using this term 2 rules that have the term at the left hand side, and you can see that it's left associative. Expression produces term plus expression, encodes this plus operator that is right associative. And to parse this grammar, we introduce a new rule and 3 new symbols. So we introduce terminal symbols, start of file or begin, and we introduce a terminal symbol, end of file, and we introduce a non-terminal symbol, except. And we succeed in parsing when we get to this non-terminal symbol. So and we add this rule, except will succeed in parsing when accept the solution when you encounter a start of file and an expression with the look ahead. Okay, so this is the notation that I will notate for representing the look ahead symbol. When the this rule only applies when the look ahead is the $sign. Okay, so this is a standard approach to making parsers that parse a certain given input. So okay, so we add this rule. This differs from the traditional approach in that this adds another terminal symbol, start of file, instead of and not only the end of file symbol. This becomes useful when we actually get to parse the input string, but we'll get to that later. And what we do with this grammar is that we produce a derived grammar based on this. We decompose for the production rules that have 3 or more symbols on the right-hand side, like this or this. We decompose these rules into multiple rules that have 2 or less symbols on the right-hand side. So for example, this rule, expression produces term plus expression, is decomposed into 2 rules. Expression produces term and parenthesized plus expression symbol. We count this as 1 symbol, and parenthesized plus expression symbol produces plus an expression. For this rule, the original rule was term produces term times value. That's a sequence of 3 symbols. We decompose into two rules that produce two symbols each. So the original rule was decomposed into 2 rules. Term produces term and parenthesized time value. Parenthesized times value produces times and value. So why do we do this? We created a derived grammar and notice like the symmetry between the traditional approach of using prefixes in item sets and this approach that uses suffixes and additional rules. So this is the biggest difference between the traditional approach and this approach. And we reproduce a derived grammar because it's easier to work with, because there are exactly 1 or 2 symbols on the right-hand side of the production rules, and this makes it easier to write code for parsing the rules. Yeah, I do think the cases turn out to be more regular and there are less cases to think about. Yes. And there is a one-to-one correspondence between the derivation of the 2 grammars. Well, intuitively, you can see why that is. And you can easily prove that the derived grammar is LR1 if and only if the base grammar is LR1. And we will create a parser for the derived grammar. In the process of proving this, you'll use the fact that there are no predictions of the form any symbol produces a parenthesized symbol followed by any other symbol, because the parenthesized symbol represents any suffix of a given rule. It can only appear at the last symbol of any given rule. I hope that made it clear. And the effect is that when you write a parser for this, when you encounter a parenthesized symbol, you can only reduce. You can never shift. And you can only reduce until you encounter a symbol that appears in the original grammar. So that is the way to understand intuitively why the derived grammar and the original grammar have the base I'll call it as the base grammar. The derived grammar and the base grammar have a one-to-one correspondence. Okay, so based on this easier to reason about rule, this derived grammar, we create a directed graph. And because there are only 1 or 2 symbols that can appear on the right-hand side, we can use a case-by-case approach. So for production rules that have only 1 symbol as its right-hand side, we could call it a unary production, and for the production rules that have 2 symbols on its right-hand side, we could call it a binary production. I used like capital letters for this, but you can this symbol can either be a terminal or a non-terminal. For example, this is a valid unary production, and this is a valid binary production. Okay, so for unary production A, because A produces B with the look ahead of T, well, you can always add this for every terminal symbol. This production rule becomes this. So B with the look ahead of T, maybe we could call this a state later on when we need to use this. Anyway, B with the look ahead of T can be reduced into A with the look ahead of T spontaneously without any help from any other states. And let's look at the binary production. A produces B. C with the look ahead of T becomes this kind of edge. So B with with the look ahead of any character that can be the first symbol of C, first terminal symbol of C. This state can be reduced into this state with the help of C with, why is this? Okay, so this state can be reduced into this state with the help of C with the look ahead of T. Sorry. So let's see some examples that explain this. So for a unary, for an edge that came from a unary reproduction, we can use this. So let's see the original rule. Expression produces term. Okay, this is a unary reproduction. Let's think about the case where the look ahead is the end of file symbol and the $sign. So expression reduces into term when the look ahead is the $sign. If you look at this, that became this edge where term with the look ahead of $sign can be reduced into expression with the look ahead of $sign all by itself. The epsilon represents nothing, an empty string. I use this symbol to represent that this can be reduced into this without any further help, without any other items on the stack. And let's look at the example of a binary reproduction that became a directed graph. Let's see. Let's look at this rule. Expression, this is a binary reproduction. Expression produces term, and this term parentheses plus expression symbol. Let's see. If we assume the look ahead is the $sign, this becomes like the original rule was expression plus the $sign produces term with the parentheses plus expression symbol, and it became this edge where term with the look ahead of plus, because plus is the only valid terminal symbol that can appear at the first character of this parentheses plus expression symbol, can be reduced into expression with the help of plus expression symbol with the term look ahead of $sign. So this state can be reduced into this state if this state, this plus expression $sign state, is at the next item of the stack. Okay. So if there's a stack and there's two items as two states, term plus and this state, then these two states can be reduced into expression $sign. Sorry. Because the grammar is fixed, the graph is finite and fixed. I hope, given these examples, the reader, the viewer, sees how this original this grammar and this graph represent the same thing. If you convert every rule that is achievable from this grammar into a graph, it becomes like this. Well, it's big and complicated, but at least it fits in a single slide. So yeah, I had to make the grammar small enough to allow this graph to fit in a single slide. Anyway, these two are the same thing. They're the same thing. Anyway, we will in the next slide we will parse an example string, and we will use this graph to help us decide whether we should like shift or reduce at every given state. So this will be used later. So now let's parse a times 2 plus 1. Sorry. If we tokenize this, and I might say the word token, which is a synonym for terminal symbol. If we tokenize this, we obtain ID times literal plus literal and the end of file symbol. Well, I might call this $1. Anyway, we're here, and we already have a started file symbol with the look ahead of ID. What we want is the state where we have the accept symbol and we look ahead the $sign. So this is what we have, and this is what we want. Are they equal? No. There are things to consider when they're equal. We'll get back to that later. Can we eventually reduce this into this? And if we carefully look at the graph, the answer is yes. And there's a unique path that starts from here to here. that ends here, and we require, as our first step, we require the expression with a dollar to be our next item of the stack. So, but we currently have nothing, so we shift, and we want expression with expression dollar to be prepared as the next item of the stack. So when we shift, the state becomes like this. Okay, so we want expression dollar to be the next item of the stack. When we shift, because the ID is shifted, this is what we have, and this is the look ahead. So the state we have is ID star. So we have an ID star, and we want an expression dollar. Are they equal? No. So, and can we eventually reduce ID star into an expression dollar? And the answer is yes. And interestingly, there are two paths from ID star to expression dollar. And before you worry that this is a conflict, this isn't, because these two paths agree which actions to take to get to this state. So you reduce using this rule, value to ID, and then you reduce term. Okay, so if you reduce this, you have from the state ID star, you obtain value star. If you reduce using rule term value, if you reduce using rule term produces value, given in a value star state, you obtain a term star state. And then there are two paths, but both paths require you to shift. So the next action is shift, and then we have a new stack item. So this isn't really a conflict. Anyway, because we after the two reduces, this state the state that I'm about to highlight, this state becomes term star, and then we shift. So the next state is like this. So this is the last item that we calculated. So we have a term star. We want an expression dollar. It's this, and we shifted. So we have what we have at the last item of the stack is star plus the look ahead of literal, which is this, and we want because we were in the process of this, and it required either parenthesized star values with the look ahead of dollar and a parenthesized star value with the look ahead of plus. We recorded as our goals. We need to achieve either this or this. Okay. So we have this. We want either of these, and we visit the graph and see that all rules require you to shift. And if we shift once more, we obtain this. We're here. Our shifted state is literal with the look ahead of plus, which is here, and what we want is either value dollar or value plus, which is here, value dollar or value plus. Now if we look at this, you see there is a path that comes from literal plus to a value plus. Now, what you realize is that this is the first time we've encountered that the current state actually matches the goal that we set earlier. So currently we have a value plus, and this is equivalent to the goal that we set earlier, value plus. Well, in an LR grammar, before each shift, there has to be a unique sequence of reduction that is actually able to shift the next terminal symbol. For example, in an LR grammar, the last state is value, and it can shift. Okay, so the last state is value. Okay. Because okay, I'll explain later, but because if you follow this step, you will eventually get to a state that can shift the look ahead plus symbol. Okay, so what I mean, okay, so I'll continue. When we have value plus, we can reduce this using this rule. And then we will have a star value, and then we can reduce once more again using another rule. And then we were able to shift the plus character. Okay, so there, we can reduce using this rule, and after a series of reductions, we will be able to shift. But because the LR grammar is LR1, we the number of the sequence of reductions that can actually shift the next terminal symbol has to be unique. Therefore, because the grammar is LR1, we have to reduce with this rule. Okay, but if you haven't used Bison and you're writing this parser and you just want to like verify if the grammar is actually LR1 at runtime, if you don't know that grammar is LR1, then alternatively we can like fail at runtime due to a non-LR grammar by using this method. We have to obtain all valid paths and compare if there's a conflict. So you either prove that your rule is LR1 using Bison, or you can just fail at runtime, like every time by verifying that there are no conflicts every time you shift or reduce. So these are the two approaches, and here, when we achieve the goal, you always can get into a state where you can shift. For example, here you can reduce value into a literal. Okay, you reduce value into literal to get into this state, and then you can reduce star value into star and value, and that achieves this goal, star value plus. And then you can use term plus, reduce this into term star and star value plus, which converts this into term plus. And then you get this state of the stack. And of course there is a path that can shift the plus character, because that is what we calculated here in the first place, right? So after a series of reductions, according to the goals we set during the stack shift process, we can always go into a state that can shift the following character. That is why following the reductions corresponding to each goal can lead to a state that can shift the next terminal symbol. And because the grammar is LR1, that state has to be unique, and that is part of why this works. Anyway, because we have a term plus, we want an expression dollar, we have to shift, and we have a parenthesize. We need as the next state to be the parenthesize plus expression symbol with the look ahead of dollar. Okay, so we shift. We have a plus literal. We want a parenthesize plus expression with the look ahead of dollar. We look at the graph. We have a path. We need another dependency, which is expression with the look ahead of dollar sign symbol. So we shift again. Okay, we shift again. This is the state that we shifted. This is the goal. We have a literal dollar we want an expression dollar. So there's this unique path, and if you there's a path with 3 reductions, and if you visit the path, you will know that you will obtain expression dollar, which is the goal of this state. So you reduce 3 times, and you reduce the reduction you reduce the reduction related to this goal, which is this. This makes you achieve this goal. So you reduce once again the corresponding production rule for this goal, and then you reduce once more. So, and that leads to the state where you wanted and accept with the look ahead of dollar, and you actually have the accept it with the look ahead of dollar. So you succeeded in parsing this. So you accept this thing, and you succeeded. So if we look at the sequence of actions that we encountered during this parse, you will see that you shifted the literal identifier. You shifted an identifier. You reduce this into a value and then into a term. And that corresponds to this. So the A is parsed as an identifier, then a value, and then a term, and then you shift, which corresponds to this star character, and you shift once again, which corresponds to this 2 character, which is a literal, and then you reduce this literal into a value 2, and then you reduce star and the value 2 into a star value, and then you reduce the term. You reduce this term and this star value into another term. So, sorry. This is parsed as a term. And then you shift once again, and you shift this plus character, and you shift once again. So you shift this 1 character, and you reduce this. That character is tokenized as a literal, and you tokenize the literal 1 into a value 1. You tokenize the value 1 into a term 1, and then you tokenize the term 1 into an expression 1, and you reduce the plus expression. These 2 tokens into a one token plus expression, and then you reduce this term and this plus expression into another expression, and then because you have the end of file, you accept this as a whole expression. So if you look at it, you'll see that this is a valid parse for this grammar, and you'll see that this LR parser can parse any string that confines with that grammar. So this is the end of the demonstration, and I wanted to share a few comments. I think this is very easy to generalize. I think this is very easy to know what is actually going on compared to the state-based approach where multiple states are merged into a state, so it's kind of hard to see exactly what it's parsing. And I think it can be generalized to GLR parsers. I think it can. I hope this can be generalized to allow empty productions. I think this can be represented more elegantly in Lisp, but I don't have the Lisp foo to demonstrate this, and I don't think I have the energy to code yet another implementation. What I'd like to see with the Lisp implementation is whether or not it exposes some other interesting information about this problem. I have a feeling that interesting things might happen when this kind of algorithm can be encoded into a neural network, where the network can learn custom rules and parse according to the new learned rules accordingly. Thank you so much for watching. And I'm not sure if I'm gonna make another video, but um um anyway, thank you for watching. I don't know what to say. Here's the repo that I implemented. I'm so tired. I have an example of a non-LALR grammar that this parser is able to parse, so that's interesting. This is the example that is demonstrated in the video, and this is the parser code. 500 lines, not so bad. I tried to make it readable. I'm not sure if I succeeded in that, but here's the parser code, and thank you so much for watching. We'll meet next time, hopefully.